In this lecture, we continue to look at completing the square. In the last lecture, we discussed quadratic functions, and we introduced the concept of completing the square, rewriting x squared plus 4x plus 7 as the quantity x plus 2 squared plus 3, or x squared plus 4x minus 5 as the quantity x plus 2 squared minus 9. Since x squared minus 6x plus 9 is x minus 3 all squared, then x squared minus 6x is x minus 3 all squared minus 9. So x squared minus 6x plus, say, 2 looks like x minus 3 all squared plus a constant, in this case minus 7. X squared minus 6x plus, say, 10 begins as x minus 3 all squared plus some constant, in this case 1. In each case, we finish off the square so that we have a true statement following the rules of algebra. If x squared minus 3x is the beginning of a quadratic, then we recognize that we need to divide the cross term minus 3 by 2 and think of this as x minus 3 halves all squared. So x squared minus 3x plus 9/4 is the quantity x minus 3 halves all squared, and so x squared minus 3x, subtracting 9/4 from both sides, is the quantity x minus 3 halves squared minus 9/4. If, for example, we have this quadratic x squared plus 4x plus 7, that's the equation of a parabola, then we can complete the square writing the first two terms, x squared plus 4x, as the square of x plus 2 minus the constant 4. And so x squared plus 4x plus 7 must be what we get when we add 7 to both sides. So that's the quantity x plus 2 squared minus 4 plus 7, or x plus 2 squared plus 3. And so our original quadratic becomes, in standard form, x plus 2 all squared plus 3. This is the standard form for a quadratic, and we can see that the vertex of this parabola is minus 2, 3. We could transform the graph of the basic parabola y equals x squared into the graph of this one by shifting the graph of y equals x squared 2 units to the left, because we replaced x by x plus 2, and then shifting the graph up 3 units because we added 3 on the outside. An extra step in this process occurs if the coefficient of x squared is not 1. How would we complete the square on something like 2x squared plus 8x plus 15? Once again, we focus on the first two terms, 2x squared plus 8x. In this case, the leading coefficient is not 1, so we factor out the leading coefficient, writing 2x squared plus 8x as 2 times the quantity x squared plus 4x. X squared plus 4x is a polynomial whose leading coefficient is 1, and so we're going to complete the square inside the parentheses, rewriting x squared plus 4x as x plus 2 all squared minus 4. Therefore, 2x squared plus 8x, which is twice x squared plus 4x, is twice the quantity x plus 2 squared minus 4, and if I multiply the 2 through, I get twice the quantity x plus 2 squared minus 8. If I begin with y equals 2x squared plus 8x plus 15, then completing the square gives that 2x squared plus 8x plus 15 must be twice x plus 2 squared minus 8 plus 15. So we have this expression. What's the vertex of this parabola? We completed the square, and we got, in standard form, twice the quantity x plus 2 squared plus 7. This is a parabola with vertex minus 2, 7. To transform the basic parabola y equals x squared into the graph of this one, notice that we replaced x by x plus 2, so we need to shift the basic parabola to the left by 2 units. Then we multiplied on the outside by 2, so that must stretch the graph vertically by a factor of 2, and then finally we added 7 on the outside, so that slides the graph up 7 units. Here's another problem. Let's find the standard form for a parabola with vertex 2, 1 passing through 1, 4, 5. A parabola with vertex 2, 1 has standard form a times the quantity x minus h squared plus k, where hk is the coordinate of the vertex, and since h is 2 and k is 1 in this case, we know that the parabola must look like this: y equals something times the quantity x minus 2 squared plus 1. But we can plug in the point where x is 4 and y is 5 and see that y equals 5 must be the same as a times 4 minus 2 all squared plus 1. We can solve for a and see that a is equal to 1. So our final answer is, in standard form, y equals 1 times the quantity x minus 2 squared plus 1. Let's find the vertex of the parabola with the graph given by this equation. Notice that the leading coefficient is 2. So to complete the square on 2x squared minus 12x plus 4, we factor the 2 out of the first two terms and recognize x squared minus 6x as the beginning of x minus 3 squared. So x squared minus 6x is the quantity x minus 3 squared minus 9. We will multiply by 2 so that we have the quantity 2 times x minus 3 squared minus 18. We multiply the 2 and the minus 9 to get the minus 18, and then we simplify to get this answer. The vertex here then must be 3 minus 14, since we are subtracting 3 from x. That shifts the graph to the right by 3, and then we subtracted 14, moving the original parabola down 14. We can then describe precisely the transformations necessary to move the basic graph y equals x squared into the graph of this quadratic. We found the standard form on the previous slide to be this, and so we must do the following transformations in this order. Notice that we've replaced x by x minus 3, so we must shift the basic parabola to the right by 3. Then after we squared, we multiplied by 2 on the right, so that stretches the graph by a factor of 2 in the vertical direction, and then we shift the graph down by 14. Now we can obtain a nice general formula for solution to a quadratic equation if we complete the square on a general arbitrary quadratic function. Let me show you how this works. Let's consider the general quadratic function ax squared plus bx plus c, where a, b, and c are unknown constants, and we're going to complete the square without worrying about what a, b, and c are. We can put this function into standard form by first factoring out a from the first two terms. So we get this expression. And then we complete the square on the part in parentheses, x squared plus b over a x. We're going to complete the square on x squared plus b over a x. It's the beginning of the square of x plus half of b over a. And so if you square out x plus half of b over a, you get x squared plus b over a x plus b squared over 4a squared. You get this expression. If I subtract that messy b squared over 4a squared from both sides, I get this expression, which involves a square and a constant term on the left, representing the x squared plus b over a times x. Let's review for a moment. We began by factoring out a, and then completing the square on the inside. If we distribute the a across the terms, we have this expression. So we've simplified b squared over 4a squared multiplying by a. And then if we get a common denominator on the last expression, we get this expression, a times the quantity x plus b over 2a all squared, minus this messy b squared minus 4ac all over 4a. This is the standard form for an arbitrary quadratic. I have taken the arbitrary quadratic and put it in standard form. Let's not try to memorize this. It's much easier in general, given a general quadratic, to quickly complete the square and get the standard form. If there's anything you might want to memorize, it's the general solution to an equation that this result gives us. In the previous slide, we took the general quadratic, ax squared plus bx plus c, turned it into this standard form. Now that we have completed the square on a general quadratic, we could ask, where is that quadratic equal to 0? If you want to solve this quadratic equation, you could use the standard form instead and solve this equation. This last equation here is easy to solve because you add that messy b squared minus 4ac all over 4a to both sides. You get this. Now divide both sides by a to get that. Notice that on the left we have a perfect square, so on the next slide we will take square roots. Alright, so we started with this quadratic. We turned it into standard form, and then set that equal to 0. We moved one constant over to the other side to create a perfect square. And now let's take the square root of both sides, keeping in mind that we want both positive and negative roots. So if you take the square root of both sides, then x plus b over 2a is this expression on the right. The denominator on the right side, 4a squared, can be simplified. Since it is a perfect square, the square root of 4a squared is 2a. So x plus b over 2a is equal to plus or minus square root of b squared minus 4ac all over 2a. And then we can solve for x by subtracting b over 2a from both sides to get that. And we combine the right side using the common denominator to get this. Now, this is the quadratic formula, and this expression is worth memorizing. In an earlier slide or earlier lecture, I said you should not memorize. Well, this is an exception. This is worth memorizing. The general solution to a quadratic equation of this form is this expression. X is minus b plus or minus square root of b squared minus 4ac all over 2a. The expression b squared minus 4ac under the radical sign is called the discriminant of the quadratic equation and is sometimes abbreviated by the Greek letter capital delta. With this notation, the quadratic formula says that the general solution to a quadratic like this is minus b plus or minus the square root of delta over 2a. In the next presentation, we examine the equation of circles.